Hello everyone, and welcome to our final project presentation for the fall 2025 Deep Neural Networks course at Johns Hopkins University. Thank you all for taking the time to join us today. For this project, our team participated in the Kaggle MAB competition, officially titled Social Action Recognition in Mice. MAB stands for Multi-Agent Behavior, and the challenge focused on automatically identifying mouse behaviors using large-scale, markerless, post-tracking data. It is considered one of the Kaggle's more ambitious scientific competitions because it tackles a real-world problem that neuroscientists face every day, and that is how do we reliably identify complex animal behaviors at scale and across different labs, different setups, and different environments. Before we dive into the project, let me briefly introduce my team. My name is Xiang Liang, and I'm here with my teammates Lijian Gong and Swarup Sahu. We complete this project under the guidance of Professor Oleg Monikov as part of the Neural Network course in the Whiting School of Engineering. With that, let's go ahead and jump into the project. Yes, so first of all, I would like to start off by giving some background information about this project, as well as the competition itself. Our team is called JHU Team 1, with the team members I just mentioned earlier. The competition itself runs from September to December, and it's a pretty major one. There is a 50,000 prize pool with more than 1,200 teams from all around the world are participating, which makes the leaderboard extremely competitive. And I also want to mention that we have given the consent for this presentation to be shared for any educational purpose after December 2nd. Okay, I want to quickly clarify a few terms that will appear throughout the presentation. Most of these terms are standard technical abbreviations, such as CPU, GPU, and TPU, which simply refer to different types of processing units. We also have RAM, short for Random Access Memory, TF, TensorFlow. It is an open source machine learning library developed by Google. We also have URL, represents Uniform Resource Locator, MSPPT, Microsoft PowerPoint, LB, leaderboard, and F1 score. It's a competition metric that we're going to be seeing in the future. And the F1 score is being calculated using recall and position metrics. Now, let's take a closer look at what this competition is actually about. So first, the challenge is sponsored by Cornell University, and the goal is to develop a model that can recognize over 30 different mouse behaviors directly from video-based post-tracking data. To support this, the organizers provide a massive dataset, more than 400 hours of footage collected across over 20 different recording systems. The diversity is intentional because it forces model to generalize well rather than overfit to one specific lab setup. One of the key difficulties here is the limited amount of label data. For many behaviors, like rest or freeze, happen rarely in the actual experiments. This makes them much harder for models to learn. So part of the challenge is to dealing with this imbalancement of behaviors and making sure the model doesn't ignore these rare but important behaviors. Another major objective is cross-lab generalization. A successful model shouldn't just perform well on data from one lab. It needs work across different environments, camera systems, and behavior recording pipelines. And ultimately, the broader aim of this competition is to automate large-scale animal behavior analysis to support fields like neuroscience and ecology. On this slide, I want to quickly go over some of the practical constraints of the competition because these rules shape a lot of decisions that we made later on. So first, every submission has to be generated inside a Kaggle notebook, and each notebook must finish running within 9 hours. And that is whether you're using a CPU or a GPU. So efficiency becomes extremely important at this point. Another big constraint is that the environment is completely offline. So Kaggle disable all internet access during execution, which means that you have to download all the packages that you're going to be using ahead of the time. CPU notebooks usually give you around 13 gigabit of RAM, and GPU notebooks give you about 16 gigabit. But when we consider how big this dataset is, we'll always have to think about running into the out of memory errors when we designing our pipelines and the models. So again, the efficiency is probably the key of designing the whole project. And we also see that at the bottom, there are some important deadlines for this competition. We have the final submission day is on December 15th, and the last day to merge team is on December 7th. Here's a quick overview of how our team performed throughout the competition. We tracked our progress across multiple modules, from Module 5 to Module 14. Over time, our leaderboard score gradually increased as well, ranging from about 0.27 up to 0.446. And along with that improvement, our ranking went up as well. So ultimately reaching 441 out of 1,286 teams. So even though the competition was extremely challenging, we were able to steadily climb the leaderboard. You can see that the number of submissions that we made grew over time, from just 5 in Module 9 and to 59 in Module 14. As we iterated more, our understanding of the data and the metric improved. So that is reflected in the results. And now on the right-hand side, we summarize how the scoring metric actually works. So the competition uses a macro average F-beta score. This metric is calculated separately for each behavior, each video, and each lab, and then averaged, so no single behavior can dominate the score. Okay, here let's see what the data looks like. As we mentioned earlier, there are really just three main parts in this dataset: the metadata, the tracking data, and the annotation data. So metadata provides general information about each video and the mice in it. So team receives a CSV file that includes things like the lab ID, the video ID, the frame rate, frame duration, arena shape, arena size, and basic labels such as the body parts are being tracked and the tracking method were being used. And next we have the tracking data, which is essentially the post data. It tells us where each mouse's body parts are located in every frame. All of this was provided in Parquet files for both the training and testing sets. Each row includes the frame index, the mouse ID, the specific body part, and its XY pixel coordinates. And finally, we have the annotation data. Annotation data captures the behaviors themselves, what a mouse is doing at any given moment, either to itself or to another mouse. This was also stored in Parquet file, but only available for the training set. Each record includes the acting mouse, which is the agent ID, the receiving mouse, which is the target ID, and the behavior type. We also have the start and the stop frame of the behavior. So together, these three data sources form the foundation of the entire competition and define what our model needs to learn. This slide is simply an example of what the metadata looks like in the dataset. Each video comes with detailed information about the recording, things like the frame rate, duration, arena shape, as well as attributes for every mouth, including strain, color, sex, and age. The diagram in the middle shows where each mouse is positioned in the arena, and the table below illustrates how those fields appear in the raw metadata files. And just to know that, this is only a simplified snapshot. The actual metadata files are much larger and contains 26 different columns of information for each video. This is the dataset overview. Starting in the top left, we can see that the dataset is extremely unbalanced across laboratories. A few labs contribute the majority of videos, while many others provide only a small number. This variation is one of the reasons the cross-lab generalization is challenging. On the right side, we can see a pie chart. The pie chart shows that almost all videos contains 4 mic, which is the standard configuration for this dataset. On the top right, almost all configurations track around 11 to 12 body parts per mouth. The middle left chart shows that video vary widely in how many behavior types they contain. Some videos include only a few behaviors, while a small number have dozens. This again highlights the imbalancement problem that we probably need to handle. On the middle right, we have the top 15 behaviors, where sniff and attack appears extremely frequently, compared to many rare behaviors like entrapment. And in the bottom right, we see that this is the distribution of the video durations. Most videos cluster around 2 minutes, but some extend well beyond that. And next, we have an example of the tracking data. We'll see in the center is a post-tracking diagram. For every frame of the video, the dataset gives us the exact pixel coordinates of multiple body parts on each mouse, such as the nose, ears, body center, and different points along the tail. These key points are detected automatically using a post-estimation model, such as Deep Lab Cut. On the right, you can see an example of the row tracking data that's being stored in the Parquet files. Each row corresponds to one body part of one mouse in a specific video frame and includes 4 variables: the frame index, the mouse ID, the body part name, and the XY pixel locations. Together, this tracking data forms the core input the model uses to understand movement patterns and eventually recognize social behaviors. On this slide, we are looking at the target variable of the MAB computation, the behavioral annotations. The images across the top show different video frames over time. For each frame, annotators label exactly what behavior each mouse was performing, and also who the behavior was directed toward, whether it was toward another mouse or to itself. The timeline diagram in the middle illustrates how these behaviors unfold over time. For example, mouse 1 might be performing locomotion from frame 100 to 180, while at the same time, mouse 2 could be performing sniff toward mouse 1 from frame 150 to 220. And later, both minds may transition into a pulse behavior starting around frame 230. So each color bar represents to one continuous behavior segment, defined by the agent ID, the target ID, the action, and the stop and start frame. At the bottom, you can see the row annotation format of the Parquet file. Each row encodes one behavior event exactly the way our model must output in the final submission.
In this computation, each submission must follow a standardized CSV format with the following columns: row ID, unique identifier for each record; video ID, ID of the video containing the behavior; agent ID, ID of the mouse performing the action; target ID, ID of the mouse receiving the action; action, type of behavior detected; start frame, stop frame are the time frames of the action in the video frames. Each row captures a single behavior instance. If agent ID and target ID are the same, the action is classified as self-directed. If they differ, it's considered a pairwise interaction. In this dataset, we work with 2 key components, metadata and the tracking data. The metadata CSV files, train and test, provide contextual information about each video and the mice involved. This includes lab identifiers, mouse demographics, video specs, arena dimensions, and the specific body parts tracked. Each lab used different tracking technologies, so the granularity of post data varies. The tracking folder contains frame-by-frame coordinates for each mouse's body parts, which we use to extract features like position, speed, relative speed, and orientation. Our goal is to generate structured data frames, either for individual mice or mouse pairs, that capture these features over time. These data frames serve as a foundation for behavior classification, distinguishing self-directed actions from social interactions. By aligning pose data with annotated behaviors, we build a rich temporal representation of mouse dynamics across diverse experimental setups. In this phase, we focus on extracting rich behavior features from pose tracking data. For self-directed behaviors, we quantify metrics like body part positions, movement speed, and orientation. We also analyze curvature and turning rates, and compute multi-scale speed statistics to capture subtle movement states. To model transitions, we smooth positional data over time, helping us detect shifts between the behavioral modes. For social interactions, we extract pairwise features such as in intermouse distances, relative speeds, and angles, which are crucial for identifying behaviors like chasing or grooming. These features are aggregated across time windows to capture rolling interaction dynamics. The entire process is implemented as a scalable pipeline that generates per video feature sets ready for training behavior classification models. This engineering step transforms raw tracking data into structured, interpretable signals that power downstream analysis. This slide showcases key preprocessing functions used to transform raw post-tracking data into meaningful behavior features. The code is designed to be both efficient and scalable. For example, we calculate speed features by tracking positional changes in body parts like the head and tail base, which are critical for identifying dynamic behaviors such as chasing or avoiding. We also estimate missing node positions using geometric relationships between the ears, helping us infer orientation and sniff-related actions. Importantly, the code is carefully structured to minimize memory usage. Temporary variables are scoped and discarded promptly, allowing Python's garbage collector to free up memory. This is especially valuable when processing hundreds of thousands of frames across multiple mice and videos. By combining precision in feature extraction with memory-aware design, these snippets form the backbone of our data pipeline for behavior classification.
Hi everyone, this is Swarup and I'll be discussing the light GBM model and our final results. So going right ahead. So our model was to use a light GBM model. So this is your gradient boosted models. Our inspiration was through a community post on Kaggle with a user who had a 26% LB for their F1 score on the test data. But we basically thought that using a gradient boosted model would be easier for understanding purposes the data, being able to have a simpler model than, for example, having more complicated and deep neural networks or deep learning right off of the bat. So we first wanted to start off with a light GBM implementation. So and we applied all of our feature engineering and pre-processing step that we had all discussed in the previous sections, but we added this on top of that, and then we focused on our main piece was on hyperparameter tuning to try to make our F1 score even higher. So this actually helped us improve our leaderboard score of 38%, which is even higher than what the original poster had was able to achieve. And this is all through a combination of having the right features, the right feature engineering, and being able to have the right hyperparameters. So we'll move towards the discussing the workflow. Now, just a little refresher on an XGBoost architecture. You take in your input data, you initialize your model, but the whole idea behind boosted trees is that you're training on the errors of so you're iteratively training on the errors of previous trees in the hopes of making each tree on every iteration better and better and better. So that's how this entire loop here is working, this iterative boosting loop. And then eventually you get to your final ensemble model, which is just the aggregation of all your previous models. So for that, we used a logistic objective. So is this happening or is it not happening? And we use stratified group k-fold for our cross validation, and group k-fold allowed us to group by video ID, and the stratification allowed us to have very similar distributions between training and test. Our class imbalance, for that, we use the scale position weight parameter to tune that. And some of the other hyperparameters here are, our learning rate was set at 0.05, max depth at 6, and our sampling at 80-20 splits. Now, one of the big things that we did was that after 10 rounds, if we couldn't improve the F1 score of our model, we would stop it in order to prevent overfitting. This is something we noticed while in our entire training process, that this was happening, so we stopped it at 10 rounds. And per fold, every time we would run through the validation steps, we would create all of our model files, all of our thresholds, and all of our plots, and we would save them on the cloud. Now, this is just the workflow, our training workflow for all the mouse behaviors. So one of the key things is that there's actually two workflows. They're very similar, but essentially there's one flow, which is looking at how the mouse or the mice act on their own. So they sometimes a mouse can act on another mouse, or a mouse can just do whatever it's doing. So for example, if it's a single in this left-hand side workflow, if it's going through that, if you're only analyzing what the mouse is doing to itself or its surroundings, then that would go under this. If you're going to look at what the mouse is doing to something, which is agent or target, then it would go through this flow, and we would train based on which category the mice would fall under. So as we've mentioned, we group the data by each of the labs and the behaviors that for the self and the pair behaviors that I just mentioned. And then we would load all the features, and then we would train and evaluate the model per behavior with all the F1 scores logged. And we would track the progress through all of our artifacts that we generated per fold. And then, as I had already mentioned, and this is the big thing to take away from this slide, is that it is between a mouse acting on itself and a mouse acting in a pair. Now, in this slide, the main takeaway here is that during certain intervals of training our data, you could have overlapping intervals between two different types of actions. So those instances also had to be, we had to figure out ways to remove those types of overlaps. And after we had removed those, we would need to aggregate all the predictions across all the behavior categories, and then we would have to pick the best the behavior that our model was most confident was occurring in each of the video frames. After that, we would then have to collapse all the predictions into defined intervals so that you wouldn't have multiple predictions per interval, right? There could only be one action per interval. And then we would fill in the missing predictions for any that didn't have any output data. And then one big thing here is if you look at the bottom right here with the top actions by F1 score, this is basically our top 15 of our actions and how the F1 scores fluctuate with the little whisker plot showing the variance. But the big key thing here is, you can see things starting to bunch up. For example, sniffing the face, genital grooming, reciprocal sniff between pairings, versus, for example, defending or attacking. And you can imagine some of these lower scoring actions such as defend and attack, they can be very similar. So it is hard to parse out if something is if someone's being defending or attacking. And plus, every lab that's doing all these annotations can have different interpretations. So one lab could think it's attack, whereas another lab could have found that same video from that other lab to be, for example, defend. So that does cause noise in the F1 scores. So some of our, some of the challenges that have already been mentioned throughout the entirety of this presentation is that, and I already mentioned this right before this, is that there's an inconsistent frame labeling by all the labs. So again, someone could be saying defend, someone could be saying attack. So it makes it complicated for us to normalize the data across all the labs. Our system memory is also limited, even with today's computing standards. On Colab Pro, we could only get in about 300 or so features. So we definitely are constrained by this part of it, because the data can be very rich. It's huge. We also had key body parts that were missing, which limited our model choices. So this is why we picked a tree-based method. And we'll get into the deep neural networks next, but those are some of the few applicable models that one can use for this project. Another big challenge is that, there's rare positive action cases. So some of the rarer aspects, some of the rarer actions, I'm trying to recall. We can even use defend, for example, right? There's not that many cases in the data where a mouse is seen defending itself all the time. A lot of mice are very cohesive, within their entire, in their arenas, right? And with all the other mice, like mice are generally friendly. So you don't see those types of actions. So when you're trying to train on these sparse actions, it makes it difficult. Now, our cross-validation results often didn't correlate with our leaderboard performance. So, our leaderboard performance might be, here 44.6, but our cross-validation could be, something higher, something lower. So it made it tricky even when we were doing this on our local machines before running it through these submissions, that we didn't know if our model was truly improving based on that. So that's near the end of our presentation, but we have a slight appendix slide, but just a brief overview. This is our references page for all the books and research papers that we looked through and cited. This is our list of community posts on Kaggle that we took a look at to help build some of the foundational blocks for our project. Now, just some things on the appendix I'll be discussing. So we had a section during the interim project where we, or the FPIP, I forget the acronym, but we basically had what's next, what's for next week. So we decided, we would have something of how can we improve this models, which is what we have here. So, as I've mentioned, one of the big bottlenecks for this entire project is that the tracking data set. So this is all of where is the mouse at any given second? Where is that mouse? Where is its ear? Where's its body, its nose, everything? Where is that? That's the video tracking, and that can help you, train to see what behavior is being occurring. But there's not almost 9,000 data sets, and if we tried to convert all of that from Parquet format, and then we would try to convert it into and just load it on the disk, it was over a terabyte, or over a terabyte and a half. And that's not even with any feature engineering. And the other, as mentioned, our max RAM is on Google Colab Pro was only less than around 13 gigabytes, I would say. So this is where TensorFlow is perfect. TensorFlow is it has compatibility with the LightGBM implementation, but it also, it basically unlocks all the deep learning that we can do using all of TensorFlow's built-in packages. So our solution here, and I've had this image here of some of our code. So our solution was to create a TensorFlow pipeline that basically directly loaded all the Parquet files. And I've already mentioned some of these advantages. One other advantage I forgot to mention is by doing this, we could train our data in batches in parallel, and this could actually use the GPU or TPUs in Google Colab. And we were able to get a Google Colab Pros subscription since we're students. Now, this is just a hypothetical slide. We still are working on implementing this on our team, but we our eventual idea with this project was to move towards using neural net models because they tend to outperform our LightGBM solution. So one of the papers we had taken a look at with Sun et al., we looked at some of their implementations and their average F1 scores, and we saw that they, using neural networks, vastly outperformed anything we were able to create using a LightGBM implementation. As you can see, they try to different neural network structures, and their best resulting one was a 1D convolutional network with an average F1 of 0.79 with variance of 0.01. That's very high. That's almost twice what we could achieve. And some of the features that they discussed that they had tried to incorporate were distances, velocities, angles between coordinates, depending on where an agent is, where they're looking at. And these are some of the things that we're already doing with our LightGBM implementation. And there, some of the hyperparameters they considered was the number of input frames, frame skips, units per layer, and learning rate. So our idea with this project, using the LightGBM helped us understand where we are. And then we eventually started transitioning towards, working on a neural net model. As of now, we haven't had any positive results. Our LightGBM still tends to outperform any of our neural net implementations, but we're hoping that this week we can finalize our model, our predictions, and then submit to Kaggle. So with that, thank you all for listening to our presentation. I hope you liked it, and I hope you learned something from it. And yeah, it was a good semester. The team thanks everyone. Have a good day.